Today we'll be looking at explicit formulas for a geometric sequence. So here's an example. It states that a of n, which is the nth term in the sequence, will be equal to 6 times 4, which was raised to the power of the previous term. Thus, to find the first number in the sequence, I can replace n by 1. So 4 raised to the power of 0 equals 1, and then 6 times 1 is 6. Next, we replace n by 2 to find the second term in the sequence, and remember the order of operations. We first do the brackets, and then the indices, and then we multiply. Now, by having a look at the terms that we found using the explicit formula, I can see that we're multiplying the previous term by 4 each time, right? So from 6 to 24 to 96, that's what we did. I don't have to use the explicit formula anymore. I don't have to plug in anything here. If I want to find the next term in the sequence, multiply 96 by 4, and that is my fourth term in the sequence. And yet, what if I want to find a larger number like 56? Well, I cannot keep on multiplying the numbers until I reach the 56th term, because that would just take on a lot of time. So instead, I will be using the explicit formula, which is very helpful in these cases. And it takes me half a minute to solve this, while it would have taken a lot longer to count all the way up to the 56th term and keep multiplying. But how do I know that this explicit formula is actually giving me the correct answer? Or even if it does, where does this formula come from? Well, here I have a similar table to what we did with arithmetic sequences, but this one is geometric. You can still build a table like this. So n, these are the positions in the sequence. So the first term in the sequence is 6, second term 24, and here's the term value. Fill in 6 as my first term in the sequence, right? Then instead of writing 24, I can also say that 24 is the same as this very first term in the sequence, 6, being multiplied by 4. Since it's a geometric sequence, it keeps on multiplying the previous term. So instead of writing 96, I can also say that it's the first term in the sequence, 6, which has been multiplied by 4, and then multiplied by 4 again to get the third term in the sequence. Okay, the fourth term, again, will be 6, the first term in the sequence, being multiplied by 4, and multiplied by 4, until we reach the fourth term. Thus, we arrive at the formula of all formulas, the explicit formula, which states that the nth term in a sequence is equal to the first term, like 6, being multiplied by the common ratio, like 4, as many times or raised to the power of the previous term number. For example, look at the third term in the sequence. We can see that it is equal to 6, the first term, multiplied by 4, and then again multiplied by 4 twice. Why? Because we're looking at the third term in the sequence, but the previous term number was 2. We can generalize that the nth term in the sequence in a geometric sequence is the first term times the common ratio, which was already multiplied by itself, or which was raised to the power of the previous term number. Here is another example. So in this sequence, we go from 8 to 4 to 2 to 1. As you can see, our common ratio is a half because we're multiplying by a half each time. Thus, I can fill that in as one of my variables, r equals 1 over 2. And then a, which is the first term in the sequence, is 8. Now, all we have to do is arrange this into an explicit formula. So the first term in the sequence, 8, multiplied by a half raised to the power of the previous term number. Unlike the arithmetic explicit formulas, this formula does not have to be simplified any further. Let's verify by inserting 56 as a term number. So I replace n by 56, 56 minus 1, 55, a half to the power of 55 is some very long number. Scientific notation was included to write that, multiplied by 8, which was the first term in the sequence, and here we can say that we're almost certain that this number is accurate. Alright, so now you know how to derive the explicit formula for any geometric sequence. See you in the next video.